This is a lesson on conservation of momentum in the unit on momentum. In a previous lesson, I had introduced the ideas and concepts of linear momentum. There's the equation for it, P equals mv. Total momentum, since momentum is a vector and follows the principle of superposition. If we want the momentum of a system, we would add all of the momentums of the individual components. And we related momentum to an external force on a system. And we saw that impulse is a force applied over a certain amount of time. And that will cause a change in momentum, a change in the motion in the system. When it comes to conservation of momentum, there's a very specific quality that happens with the external force. If there's no external force on the system, right? If I plug in 0 for an external force on the system, that means overall there was no change in momentum for the system. This is what we call conservation of momentum. When the initial momentum, right, P, we would say 0 equals P final minus P initial. And when I solve that equation and separate them on either side, we get the initial equals the final. And this is the conservation of momentum. And you can see, like conservation of energy, there's an initial state and a final state, and we will draw sketches in our pictures to represent the initial and final state. And what we really need to double check, you can't just use conservation of momentum whenever you want to use conservation of momentum. You have to check this condition. You have to ask yourself, is there an external force on the system? And if not, then I can use conservation of momentum. I often see students knee-jerk and apply conservation of momentum without really doing that a priori analysis. Are my assumptions met in order to use conservation of momentum? If you have an external force, then this term isn't 0 and this equation isn't true. So watch out for that. I did choose a couple of examples that are pretty straightforward in applying momentum and conservation of momentum. The first problem I have here is a boxcar. Boxcar 1 moves down railroad tracks with a speed. It collides and couples with another boxcar 2, which is initially at rest. Okay, so I have an initial position, initial situation. Together they move down the track at V final, so I have a final. Let's go ahead and do our initial and final situations here. Here's boxcar 1 and here's boxcar 2. V initial, V2 initial equals 0. It says this one's at rest, which is initially at rest. And V1 initial equals 6 meters per second. They both have a M1 and an M2, but I'm going to leave that out. Let's make this guy going in this direction. And I'm also going to assign a coordinate system, right? That's the correct thing to do when I'm accounting for vectors. I need to assign a coordinate system and make sure that the signs are there. So this is the initial state. I'll do a final state down here, and you'll see why initial and final, and just like with energy, the objects have moved and their motions have changed. So let's look at it later. When it first hits, when 1 initially hits 2, 2 is going to be about in the same place, right? They're going to move down the track. They say V final equals 2.4 meters per second, and they're together. And you can put that maybe down here, M1 plus M2, as opposed to an M1, which is separate than M2. When I look at this situation, we're on railroad tracks. I'm going to assume, and they didn't mention it, that there's no friction between the rollers and the track on those box cars, that there's no friction, there's no train that is in front, there's no people, there's nothing going on that would cause an external force on those two. Of course, there's a force between them, but that's an internal force, and I don't have to take that into account. So I will write up here, force external equals 0. So I checked my condition for conservation of momentum. So I can write down P initial equals P final. So over on this side, I'm going to sum up the initial momentum. I have M1 V1 initial, which is a vector, plus M2 V2 initial, that's also a vector. And then afterwards, I'm going to have P final, and I'm going to note that they're connected together after the collision. So I'm going to put them together as a system after the collision, and they are both moving with some v final together. Okay. I am going to note that the initial speed of 2 is 0. And over on this side, I'm left with m1v1 initial, and over on this side, I have m1 plus m2. It says, what's the mass of boxcar 2? I'm just kind of keeping in mind what my unknown is, what I'm going to solve this equation for, and it's m2. So in my next algebra step, I'm going to distribute that v final. So I'll get m1 v1 initial equals m1 v final plus m2 v final. Going to isolate m2. So m2 equals, well, I'm going to move m1 over to this side, and I can factor it out. So you can do this algebra as you please, minus v final. And then I have to divide by v final to get m2 by itself. So when I plug the numbers in, let's see, m1 is 4,000. V1 initial is 6, V final is 2.4, and then I will divide by 2.4. Okay, so it looks like weird numbers going on, but this comes out to a nice round 6,000 kilograms. This is a straightforward application of conservation of momentum. I drew an initial and final picture. I assigned a coordinate system. I double checked that the external force is 0, and then that allowed me to set P initial equal to P final. Followed through my algebra, and I solved for my unknown. I have a second problem, very, very similar. It's the skater's problem. You may read it and pause it and maybe see if you can do this problem on your own, and then follow up watching my solution. It says, during an ice show, 60-kilogram skater leaps into the air and is caught by an initially stationary 75-kilogram skater. What is their final velocity? Assuming negligible friction. Okay, I'm seeing that this check that there's a no net force on the system. They're saying negligible friction on the system. And that the smaller skater's original horizontal velocity was 4 meters per second. So I'm going to get an initial and final going. So let's see. Here's a skater 1. M1, and has an initial velocity V1 initial equals 4 meters per second. There's 2, here's M2, and this person is just standing there, going to catch this one. Okay, so here's the initial. Afterwards, I'm going to assume that they're sort of like right after the second skater catches the first, right? This mass is going to be m1 plus m2 together, and they're going to move with some final velocity, which we don't know. And I'm also going to remember to assign a coordinate system, positive x in this direction, so that I can keep my vectors attended to. I'll do my check. Is the external forces on the system equal to 0? Well, it says negligible friction. I'm on ice. There's no forces on either skater outside, so I will say F external equals 0. That's a check. So I can write down P initial equals P final. Initially, I'm going to have the two separately, so M1 V1 initial plus M2 V2 initial. We're probably both thinking in our head one of those terms is 0. And then afterwards, they are together and moving with a single speed. All right, so indeed, V2 initial is 0, so we're going to cancel that term out. And we will solve for the final speed. What is their final velocity? So V final will equal M1 V1 initial with the vector on it over the total mass. So it looks like it's going to slow down. We expect it to slow down. There's two masses together. That initial momentum that only the smaller skater had is now being contained by both of them together, so the whole thing will slow down. So let's write this out here. We're going to have 60 times 4 divided by 60 plus 75. And when you multiply this out, you get 1.7 repeating, and this is a velocity meters per second. You can go ahead and run through the, what do you get, kilograms over kilograms times the velocity, so you get a velocity out.